Okay, so today what we are going to discuss is, let me put this in presentation mode. Give me a second. We will be discussing, shuffle, partition, and couple of ways to improve the performance of a Spark job. So I am sure you would have, if you are doing the work either every week or whenever you get time, you're reading about Spark. You might have heard about, you might have read or heard about shuffle, already, and you might have some idea about shuffle also. So, but we'll start from scratch. What is shuffle, and why it happens, and what is the consequence of this? So shuffle occurs when data is rearranged between partitions. So I'll keep iterating one point. Partition in Spark means one partition in Spark means one task. In Spark, task and partitions are having one-on-one relationship, and task is part of an executor. Task runs inside an executor. So one executor can have one or more than one task. An executor itself runs inside a worker node. One worker node can have one or more than one executor. So keep that picture in your in your mental mind, so that when we talk about partitions, that it's inside one executor there is one task, and that task is related to one partition. So when data moves across partitions, then it is called shuffle. It happens when transformation is required from other partitions. For example, you are summing some value using group by, or I have some other functions which you use, which will for sure trigger some shuffle. So you have 10 partitions, you are grouping by, let's say some city, and you are, and summing up the value. And let's say city has there are only 3 distinct cities. So the data from all these 10 partitions will cross, will move over the network from these partitions to some other set of partition. So that will involve, that is a shuffle. So this is what I just explained. Spark will gather data from each partition and combine into a new partition. It's likely to be in different executor. Shuffle is a performance bottleneck because processing is halted as data is transferred or returned to the disk. So when data is getting moved across the network, Spark knows that data is still getting moved. So Spark can't do the processing because data is still getting moved to wherever the data should go to, and Spark waits for that, and that deteriorates the performance. We should try to reduce the shuffle. We should try, if possible, we should not have any shuffle. But in practical world, in production systems, it's not possible sometimes. So you should try to reduce the number of shuffles if you can, or you can try to reduce the data which is being shuffled. And there are some techniques which we'll discuss over the course of these sessions. This is just one pictorial representation of this shuffle. So what this shuffle does is, let's say you are reading, just give me a second. I want to open the chat in case someone is asking the question. So what this, let's say you are reading that you have read this data from some, text file or database or wherever you read it from Parquet or wherever you read it from. But the point is now data is in Spark partitions. And you write this data, you as part of your business processing, you repartition your data and something, and then you write it. So the data which was in this partition, in these partitions, some portion of this data from all these partitions is in one partition while writing, in different partition while writing. So these are the different storage, different way the data has been written. So the point here is that in each of these block, if you are talking about HDFS, while writing the data from multiple partitions, ended up going into one block of HDFS, just to help us understand. And when you're reading it, so you want to read it back into the similar partitions. So you will again, when you read it, then the data will, when you read it, you will read all of these partition executors into the memory. And now you want similar partition to be there. So you will repartition or apply some function which will end up, shuffling the data. So data from each of these executors will go into different executors, then is how the shuffle get cast. So in when you look at the UI, Spark UI, so one of the things you should do is, as an homework, let me write it there, is so that I also don't forget. So homework is look at Spark UI, and we'll have big session of Spark UI also later. So when you look at the Spark UI, and you can look at the Spark UI even if you are running in a Spark shell also. So run the Spark shell. When you run the Spark shell, it will show you while starting up the Spark shell itself that this is the URL. And once you see this URL, it will tell you the Spark UI URL, and it will show you that URL. You can copy paste that URL into the browser, and it will show you the UI, Spark UI. And if you run some processing, if you write some line of code over the Spark shell itself, which triggers shuffle, like we have discussed one in the last session, where we're reading RDDs and joining RDDs and all those things, right? So they were triggering the shuffle. So if you execute that on Spark shell and refresh your UI, you will be seeing something like this. So this is stage 0. So shuffle means a new stage. So if you have 2 stages, that means 2 shuffles have happened, or more than 1 shuffle has happened for sure, correct? So shuffle causes a new stage, of course. The total number of tasks of your Spark job will be the sum of each stage. How many stages you have? Like you have 3 stages here, and the number of partitions in each stage. As I said, right, one partition is one task. One task is one partition, and so you have 3 stages, and each stage you have let's say 3 partitions. So it becomes total number of tasks will become 9. If you have 4 stages, in first stage you have 2 partition, in second stage you have 3 partition, in third stage you have 3, and in stage 4. So 4 plus 4, 8 plus 6 becomes 14. 14 becomes your total tasks. And we'll go into this, and this, when you see, sometimes if you are lucky and if you are able to design your job where you see only this column, this can have many rectangles here, but you will see this column, that means you have only 1 stage, that means no shuffle has happened at all. But if you see more columns, that means these are all result of shuffles. We'll come to I will write these questions in the quiz, so you can take that quiz offline. What we're going to do now is today and in the coming session is we're going to spend some time on understanding some RDD functions. We'll spend some time understanding the data frame functions. While we do that, keep in mind that we should avoid using RDDs, because the catalyst optimizer doesn't work, doesn't work on RDDs. We should try using data frames only, data frames or data sets. But sometimes you have to use RDD. You can't avoid using RDD. It depends from business cases to business cases. So if you have to use RDD, you should be aware of what are the functions you have in RDD. So because we are going to the Spark course together for the first time, so we'll go, just for the sake of completion, we'll spend some time going over the RDD functions. It might so happen that you will not be using much of it in your when you write your Spark code. But if you know these functions and you might have ended up creating RDD, then you will know what are the tools for RDD. In tools, when I say RDD tools, I mean RDD functions you have at your disposal if you have to deal with RDD. I think we discussed map and filter already. It's just a repetition, and I will just explain this example which I have written here. So we all know what is transformation action, right? Transformations are some business processing you are doing over your data, whether it is map, doing some calculation, filtering, doing some massaging of the data. And action is, let's say you're saving into file, you're displaying some records, you're saving into database and things like this. So that becomes actions. Transformations are lazily evaluated. Unless an action is there, transform won't get executed. Any transformation will not get executed. The moment you have an action, once that action starts, then it will start transformation from the beginning, and at the end, action will get triggered. will, the transformation there most, there are many transformations, but I will give you example of map and filter. So map takes a functions, apply this function on RDD because we are discussing about RDD. And by the way, the same thing exists for data frame and data set also. It applies to each element in RDD. And the result of function becomes a new value of each element in resulting RDD. So let's see how it works. So let's say I have an array and I parallelize, I create an RDD. So this is all on Spark shell. I have written this code. So you create an RDD of this array. Now what I do is I say over this RDD, invoke the map function. And what is going to happen in the map function? What is this n? What Spark will do is this is an, each element of this RDD, each element of this RDD. In this case, it happens to be an integer. So each element of this RDD will be passed as a parameter. So first time it will pass 2. And what we are telling, what to do with this 2, I'm saying, we are saying 2 plus 2 multiplied by 2. We're just squaring it up. So it becomes 4. So then Spark will take another element of this RDD, pass to the same function, it becomes 16. Then 36 and 64 and 100. That's how it works. So on each element it works. So that's how map works. Now, one thing to note is, I think I asked this in the quiz also, and I'm just reiterating here is, we are modifying this RDD. This is an initial RDD. You do any transformation of this RDD, you will never be able to modify this initial RDD. Anything you do over this RDD, it will end up creating a new RDD. Same thing happens with data frame and data set also, because those are immutable. So once you create it, then you can't modify it. It just, anything you do, it will end up creating the new RDD or data frame data set. Filter, I will explain. I think you know filter already, but I will explain it again. I think I had some file where I had, let's assume this is a file. It has many lines, and it has names of the people in each line. And what I wanted to do was, I wanted to get, only the line where my name appears, for example. So I read this file, I applied the filter, and each line is getting passed as a filter function like in map. So in this also, in an RDD filter, you are passing each line of the file as a parameter. And then what I'm doing is, this should return a Boolean because it's a filter function. So this should return a Boolean. And then here I'm checking if line contains RDD. If it becomes true, then that becomes part of the new RDD, which is data. Then I'm collecting the data. Collect is another action. So I'm collecting the data, and it prints only the line where my name appears. So in RDD, there is no versioning mechanism. It is just that anything you do over the initial RDD, it will end up creating a new RDD at all. Right? So you will have, if you are doing 3 transformation, let's say you read the RDD, first RDD, which is this. Here I'm doing 1 transformation, it becomes an RDD. If I do another transformation, it becomes 3rd RDD. If I do another transformation, it will become 4 RDD, 4th RDD. So likewise, I'll have all the 4 RDDs. So any RDD you cannot modify at all. It's just immutable. So this is what I explained. Like, this is the line I had, and I just wanted to check where my name is there. So this is just a sample data. This is again a reiteration of that. I just copy pasted some one example multiple times. Now you read about map. Now what is map partition? So map partition is a function which we use to improve the performance. And I will explain with an example. Let's say you are writing and it is just one example, but you can use map partition for any relevant business logic you might have. So the example goes like this. Let's say I'm getting some input data, and that input data has, let's say, the currency in dollar. And my Spark processing is, I want to convert that dollar into, let's say, Indian rupees. And one line which has, many columns, and one of the column is dollar. And I want to convert that dollar, and I have to process that line, and I have to take all the columns in that line. But only the extra thing I'll be doing is I'll be adding a new column, and that new column will be like, current amount in rupees. And what that, Spark processing will do is, it will take the amount in dollars, apply the conversion of to rupees, and then save that as a new column to that record. And it will keep doing the same thing with every record. Now to do this, I have to find the conversion rates from somewhere. Let's assume for our business use case that because that every day the conversion rate from dollar to rupees changes. So let's say that information is stored in some MySQL table or any RDBMS or any file or any third-party system. Ideally, it is stored somewhere outside. Now, Spark needs to connect to RDBMS system, for example, and it has to connect to RDBMS system and run a select query over that table which has this conversion. Now, let's take an example. I have this file which contains 1 million records. 1 million is 10 lakhs, by the way. So 1 million 10 lakhs records are there in that file. Now, and let's say I have 100 partitions. So 10 lakhs divided by 100, it becomes 10,000 records in each of these 100 partitions. Just to keep our calculation simple, let's make that assumption that you have 100 partition and 10,000 records in each partition. Now, one way you could do was, you could fetch in your driver code the MySQL. You can select the query. You can connect to MySQL, fetch the record of that record has dollar to Indian rupee conversion rate, and you can broadcast it. That could be one way. But let's say your business problem is such that you cannot use that in broadcast variable, for whatever reason. Let's not discuss that reason because I want to explain the map partition. What you have to do as part of your business processing is that when your Spark job is running and data is partitioned over these 100 partitions, you have to go to the database from each partition and get that value, the reference value, in this case, dollar to rupee conversion from the database. Now you have 1 million record. So ideally, and these 1 million records are spread over 100 partitions. So you will be connecting to the database 1 million times, because for each record you have to get the value, the rate. That's how your business logic is. But then connecting to database 1 million times is not right. What you could do is you could give me a second, I'm getting call. What you could do is you could connect to database once for each partition. You have 100 partitions, so you can connect once for one partitions. So you will be connecting 100 times to database. Instead of connecting 1 million or 10 lakh times, you will connect to database 100 times, one for each partition. If you want to do that, then you have to use map partition. So I'll just read it out loud just so that everyone understands it. So it is similar to map, but runs separately on each partition. It is used for use cases like create connection to DB only once per partition. Without map partition, DB connection for each row might be needed. The example which I gave, right? There are 1 million rows, so you will be connecting 1 million times. But with map partition, 1 DB connection per partition is needed. And so once you get this data, you can save in your map partition function all the rows in that map partition, can use it. It does not require shuffling, as partition as a whole stored on a node, and we'll discuss about partition in the coming slide today itself. One partition in Spark never crosses a boundary of a node. It is stored on one node only. So whatever operations you are doing over that partition, it gets executed on that node itself. So it does not cause any shuffle. Once you write the map partition function, the input to that will be an iterator. It has certain input parameters, and one of the parameters will be an iterator. That iterator will have all the records which are there in that partitions. So the example which I gave, there are 100 partition, 10,000 record in one partition. So when you apply map partition function, when that map partition function is running on partition 1, for example, it will have the iterator which will contain 10,000 records on partition 1. If the map partition function is running on, let's say partition 2, then the iterator of that will have 10,000 records from partition 2 itself, and so on with the rest of the partitions. Now the output also, because you have to process, there are 10,000 partitions, you are processing each record one by one, and you will be outputting possibly 10,000 itself. more often than not. It's not necessary you get 10,000 input, you return 10,000 output. You can skip some records also, but more often than not, you'll be returning the 10,000 output also. So iterator, the output will also be an iterator, which will contain your output, which is the output of your logic, which you have put in your map partition. So now question is, there's one question which got asked by Dhruv is, if I do not have to connect to a DB, I am fetching data from data lake, then it is fine not to use map partition. Yes, then it is fine to not use map partition. But when you are connecting to a database, you think about the business scenario. If there is one function, there is some functionality which does not change from record to record. It is same for all the records. Then maybe you do that once in your map partition. If it changes from record to record, yes, then you have to do record by record. But if it is if you want to get it done once, then use map partition. Another question is, can we use connection pooling, or that doesn't make sense? Of course, anytime you want to connect to database, you have to use connection pooling, but that, that is tangential to what I'm trying to explain, right? When you connect to database once in map partition, at that time itself, you will be using connection pooling anyway. Okay. This is one small example of map partition I have written, just to explain how that map partition will work. So I have, I am parallelizing integer 1 to 9, and have said this 3 means number of partitions I am telling. So integer 1 to 3 will be in one partition, integer 4, 5, 6 will be in second partition, integer 7, 8, 9 will be in third partition. Then what I'm doing is I'm saying this, I'm applying map partition. Now imagine there are 3 partitions. So this function map partition is running parallelly on each of these nodes at the same time. And on the first node, this iterator will contain 1, 2, 3. On the second node, this iterator will contain 4, 5, 6. On third node, this iterator will contain 7, 8, 9. And what I'm doing with that iterator is I'm saying just multiply it. Now remember one thing which I'm doing here. I'm saying iterator.map. I'm not going over all the records, 1, 2, 3. I'm going over the first record itself. No, sorry, I'm going over all the records, my mistake. So I'm going over all the records here, and I'm just printing the output. So, in 1, 2, 3, it becomes 1 for 9. In second node, it will become 16, 25, 36. And so with third node, 49, 64, 81. This is one example. I think I have another example of my partitions, which which explains it in a better way. Let's see. I think it's here only. You could try this at home. Let this be a homework. You could try this at home in your week. So what I do is I take only the first element for each partition, and and I just say collect it. So it should print 1, 4, and 7. So try this out, because on each node, 3 partitions are there, which means there are 3 tasks on each. And for simplicity, by the way, I'm saying one task is on one node, just to help us understand. But it is not necessarily that one task, one node will have only one task. One node can have 2 tasks, or 2 partitions are also running. But just for our discussion's sake, I'm saying let's assume that one node has 1 partition and 1 task running. And now we're going over some RDD functions, and I will be explaining those. What I would request you to do is, whatever an assignment I will create in Azure, you do that, but try your hands on this also. See, when you see something and you just read something, you will forget, and it will not click in your mind for it will not stay in your mind for a long time. And while reading itself, you might miss some things, at least when you are dealing with programmings. So I will encourage you to write this yourself, this distinct function yourself, in addition to the assignment. Just go through these PPTs. You have the PPT in the Google Drive, and write this yourself. So distinct is basically, you all know, if some people have worked on SQL, you all know what distinct is. Basically, it is do duplication at the end of the day. So I have this SK repeated twice, and I think CD repeated twice, and things like this. So I create an RDD out of it. Then over this RDD, I do a distinct. So now keep seeing this RDD 1.distinct ends up creating a new RDD. So I print I get this data from this new RDD, and you'll see the unique values are coming here. So that's RDD distinct. The question is, whenever the parallelize function execute, does it mean it's, yeah, This is the parallel function. See, this generally used for your testing or something. In production, I have not seen people using parallelize much, because data in production, you need data from your Parquet file or ORC file, whether it is on HDFS or S3 or blob storage. But yes, when I parallelize, then it creates an RDD. Now RDD union, it's like SQL union. You have two relations and you unionize, it becomes one relation. Same thing with RDD. I have this first RDD consisting of these integers 1 to 5, second RDD consisting of 7 to 9. Then I apply union, first RDD union, second RDD, and I get data for all of this RDDs together. That becomes my final RDD. Here also you will see any operation over any RDD ends up creating a new RDD. RDD intersection, it is common finding the common elements in both RDD. It removes a duplicate. But because you're doing intersection, so there might be some shuffling involved. So it has impact on the performance. So first RDD is between 1 to 9. Second RDD is only even numbers, 2, 4, 6, 8, 10. When I try to get a first RDD intersection, second RDD, I am getting only whatever is common, like 2, 4, 6, 8, 10 is not here, so I won't get 10. So this is what I get for intersection. Partition, sorry, this is not printed properly, but idea is that I apply partition over this. Partition this, I say first RDD, partition second RDD, and it gives me the another RDD, and that will be of type int in this case, because I have one element. If I do partition of first RDD and second RDD, it's like SQL partition. This first element will be joined with all the elements here. This element will be joined with all the elements here. This element will be joined with all the elements here. That's how partition works, and that is what you are seeing here. Now we'll discuss partitions. This is an important topic. If you get mastery over partitions, and next will be data set and data frame, you get mastery on this, and you need not be master, you get a grip on this, partitions and data frame and data set functions. I think you are good in Spark. You can claim yourself to be good in Spark. So when I will go through these partitions, but what I will encourage you all to do is read about this yourself offline also. Write some programs, read more, and understand and get a good grip on this concept of partitions in Spark. Partitions are created by default without programmer's intervention. If you don't give anything, any information related to partitions while reading the data, for example, the Spark will create some partition for you already. Like we discussed in HDFS, 1 GB file with 128 MB, it will create 4 partition out of the box for you already. You don't have to do anything, it will automatically be created. Same is the case when we read about reading from JDBC, right? There are ways to, see how many partition can be created, but there will be some partitions created for you, even though you might not specify anything. This is what I just said. By default for HDFS, a partition is created for each HDFS block read. There is one-to-one correspondence between partition and how data is laid on HDFS. This is what this point meant actually. But although you might not have control, if you don't give anything, Spark will create partition. But you can repartition the data. There are functions which Spark provides, which allows you to repartition data, and it gives you quite a lot of flexibility there. You can partition without specifying the column name. You can specify, and just give the number of partitions. You can specify the column name, over that partitioning can happen. You can specify the column name and the number of partitions over the partitioning will happen. So these are the options there, which I will explain you in the in the coming slide. So let's say this is a pictorial view of what just explained. So let's say this is the data in HDFS. So 1, 2, 3, 4 blocks are there, right? This is one big HDFS file, but first block of HDFS file contains this, second block of HDFS file contains this, third contains this, and fourth contains this. When you're reading this, see, this first block goes into the one task on one worker. This big rectangle represents one worker node. This small rectangle lies outside. This rectangle represents executor. So this and this small, even colored rectangles inside this are representing the partitions or the tasks. As I said, partitions and tasks are same. So first block goes into this task or this partition. Second block goes into this partition. Third block goes into this on different worker node for sure, and in different executor. Fourth goes into different worker node and different executor here. So this is how the data is read into the partitions. Now there is a concept called split size. You don't have to spend much time into this, but I will, this is a formula. I took this from the Spark code, by the way. I went to the Spark code and pasted this formula here. But then this example I gave myself. In reality, what this is trying to say is this, that if your file size is less than your block size, let's say block size is 128 MB. If your file size is less than 128 MB, then what will happen? So it will create a, let's say file size is 60 MB, then it will create partition of 60 MB only. The data in that partition will be for 60 MB. But let's go through this anyway. The split size, if anyone of you have come from the MapReduce background, you will understand what split size is. So one split size here in the Spark term, you assume one split size is one partition, right? If it helps to understand. So one partition, which is one split size, is equal to minimum of these two. What is the first one? Default max split size is default to 120 MB. And what is the second one? The second one consists max of this and this. What is first one? Open cost in bytes. Open cost is byte depends upon total bytes divided by default parallelism. And what is default parallelism? Sorry, open cost is bytes. My mistake. Open cost in bytes is this, default to 4 MB. And then maximum of open cost in by 4 MB or bytes per core. What is bytes per core? Total bytes divided by default parallelism. What is default parallelism? It is a number of executor cores multiplied by the number of executor instances. So let's take one example. Let's say you are reading 9 GB file, and you can define this property while while starting the Spark job. During the Spark submit itself, you can say Spark executor core equal to 1, and the number of the num executor also you can specify. And I will there's a link on the Spark website, and if you Google search Spark configurations, that link will be first or second, and it has all the configurations which Spark has. So out of that, these are the two configurations which are mentioned here: executor cores and the executor instances. So its multiplication of that becomes default parallelism. So I have 9 GB file, 1 core per executor and 3 executors. So default parallelism is this: executor cores multiplied by executor instances. The cores are 3 and 1 core per executor, so it becomes 3. Default parallelism becomes 3. Bytes per core, total bytes divided by default parallelism. So total bytes are here 9 GB. So I'm keeping it 10 GB or 9 GB here. I forgot to change it here. 9 GB divided by 3, it becomes 3 GB. Then max, I'm applying this max of this open cost in bytes or bytes per core, and a max of 4 GB and 3 GB is 3 GB is maximum. Then minimum of 128 MB and 3 GB becomes 120 MB. That's how one partition is get decided in Spark. And mostly, we don't have to debug this further. Sometimes we see, only thing when we are applying the performance, when we are looking at the Spark job for performance reasons, we look if there's any variable which can be broadcasted so that joins can be avoided. These are some performance techniques. If you're reading data from, let's say, from data source, whether it's Cassandra or MySQL or Oracle, you check whether the predicate push down is happening. And I'll tell you what predicate push down is when we come to the performance. But at high level, what it means is that when you're firing a query in a table which has 10 million records, and your query is supposed to return only, let's say, 10,000 records, then the execution of that where condition and filtering should happen at the DB server level itself, so that not all million of records travel over the network. So if that happens, you will see in your plan predicate push down is equal to true. And I will show you the output of that plan in the maybe in next session. I have that in my slides. So these are the things you take care. The idea I explain all of you that more often than not, you might not need to worry about it. Sometimes when you have some job which is which you have to debug and figure out everything, at that time you might need to able to look at it. Generally don't. This is what I explained earlier. Partition in Spark don't span multiple machines. Every node contains one or more partitions. So one node can contain one or more partitions, but one partitions cannot cross the boundary of a node. This I already said, one task per partition is assigned. If you want to know how many partitions you have, you can see this RDD dot partition dot size. It will tell you this RDD spread over how many partitions. Here I have only few integers, so it is telling only 1/1 partitions. But in case you are debugging and you want to check how many partitions this data is spread over, these are the functions you can use. There's a question: if we specify the resources, then what will be the role of yarn? So yarn has to give those resources, right? When your Spark job runs, when your driver starts on an application master, the driver will take these configurations which you have passed and give it to yarn, and yarn will tell you that you are asking for, let's say, I think you're referring to this screen, you're asking for 3 executors and 1 core per executor. So Spark driver is going to take this information to yarn and tell, I want 3 executors, and 1 for core. This becomes simple because I have 3 executor, and each executor should have 1 core. So yarn will be able to tell you on host 1, host 2, host 3, you run 1 executor each. So that's what yarn will end up doing. You can repartition your RDD. Repartition will involve shuffle more often than not, and we'll discuss about that later. The repartition method can be used to either increase or decrease the number of partitions in a data frame. The value, this is an example I'm giving. Let's say you're reading 1 to 10, and I'm just converting to DF and then repartition. By the way, this is available in RDD also. We were discussing RDD function and ended up using DF, but in RDD also you can use repartition and you can specify the number of partitions. And then the same thing, you print RDD.partition.size, you will see the partition size is 2. Repartition, this is what I discussed. Once you have read your data, you can repartition your data into multiple ways. One is you can give 1 or more than 1 column and to repartition. So Spark will repartition your data on the list of these columns. You can pass columns in this way or this way. This is the scalar functionality, but similar thing will exist in Python also. You can tell the number of partitions and the columns together, that these many partitions you create, but based on these columns, this can be 1 or more columns. It need not be more than 1. It can be 1 column also. You can pass this information in 2 ways, as a sequence or the list of columns. Or if you don't have any preference of any column, you just want data to be distributed across more partitions or less partition than what you have, then you can just pass the number of partition without passing the column names. This is what I have tried to do. This is some user info. I created some user ID and first name, last name, email. This one sample data. Another data is user transaction, user ID, the date, the transaction amount, and the city. I've used this in different. I uploaded this, and I read one file, read this user info, get the number of partitions by reading from HDFS also. So I uploaded this to HDFS. You can see the HDFS here. I read this and then I checked the number of partitions. It came out as 1. Now, internally when you repartition data, right? Depending upon the type of data it has, Spark will decide whether to use HashPartitioner or whether to use, there are 3 partitions. One is HashPartitioner, there is range, second is range partition, and third is custom partitioner, which you can build on your own. So, I was looking at the Spark code last week, and I realized that, when you call each of these functions, internally Spark is trying to figure out which partitioner to invoke, whether HashPartitioner should be invoked or whether range partitioner should be invoked, and things like this. And if you're interested, you can go to the Spark, Spark code is available on GitHub. It's written in Scala. You can check out on your local, open in your ID and go through the Spark code yourself. It's all open source. So another thing is, the HashPartitioner. So I'm just trying to explain what is HashPartitioner is. HashPartitioner is, if you want to use HashPartitioner, you should have a pair RDDs. So if you have pair RDDs, then over the pair RDD, how HashPartitioner works is it will create the hash of the key first. And then it will have the, you have given the number of partitions, for example, right? So it will divide that hash code by number of partition, and whatever remainder you get, that becomes your partition number. If you have used the modulo functions a lot, you will understand what this is. I'll explain you with an example. Let's say you want only 3 partitions. Now, any number in the world you divide by 3, your remainder will be between 1, 2, and 3 only. You cannot have remainder more than 4, more than 3. Let's say your remainder is 4, then you divide it by 3 again, it becomes 1. So any number you are dividing by 3, for example, will get a remainder either 0, 1, or 2. Right? So and because I have specified number of partition as 3, so whosoever hash keys are remainder by 3 is coming as 0, those go to one partition. Whosoever hash keys remainder, when I say remainder, whosoever hash code value divided by 3 has a remainder as 1, those go to partition 1. So I have 3 partitions, 0, 1, and 2, and I have values. Hash key can give any value. I have millions of records, and each of those records, it's a pair RDD, it's just key and value. So I create a hash of the key and divide it by 3 for the first record, and let's say remainder came as 2, so it goes to partition 2. I took the second record, create the hash of the key, divide it by 3, remainder came as 0, it goes to the 0 partition, first partition, which is 0, and so on. Correct? So I have tried to explain that here. So I read this user info table, and I split this info, split that. I should be comma here, not blank, it should be comma. So I split this and take the first element. So what happens here is, I have this user info complete record. I make user1 as the key, and the value is again the complete record itself. For the second record, user2 is the key, and the value is complete record itself. So that's what I end up doing here in my HashPartitioner. Where did I go? And then this is the key. So this becomes my key, user1 becomes key, and the complete record is the value itself. And then I partition it by, and I say HashPartitioner, and I give the number 9. So it will partition, it will split this data into 9 partitions. Now there's a catch here. I will tell you what that catch is, but with an example later. So read this, I create a pair RDD, and over this pair I say partition by, and say use the HashPartitioner to partition by, and these are the number of partitions you should use. It will give me the number of partitions as 9. Now each of these 9 partitions need not have, there will be some partitions which might be remain empty also, because that's the implementation of HashPartitioner. It does not guarantee the data will be there in all the partition it has created. So some partition will remain empty, and some partition will have more than one record, more records than the other partition. So I'll show you an example as well. So he's saying, so the hash key details is stored with the driver. It is stored internally with the Spark program. So when we discuss about the Spark memory, how the Spark memory works, you will know where this information is stored. Again, I think I am trying to use the HashPartitioner here, or this is what I just covered. I have tried to explain in little detail here, right? So I've given the HashPartitioner as 9. Now what I want to do is, I want to go, so it has created 9 partitions for me here, right? So for each of these partitions, for this RDD, which has 9 partitions, for this RDD, I go for each partition. So here I'm saying for each partition. So it has created 9 partitions. So this will be there, this will be executed for each of the partitions. Then within each partition, I am saying there are whatever number of records you have in that partition, print those records, right? This P for each is, this P is for each partition. If there are 9 partitions, then there will be 9 such P's running parallelly on each of the partitions. And within one partition, there are records, and P for each means is going over the records within each partition. So that's what is happening. So on partition 1, I see these records. Partition 2 is blank. Partition 3, I see these records. Partition 4, I see these records. Partition 5, I see these records, and so on. Right? This is how it is working. Generally, you don't have to deal with creating your own HashPartition or something, but it's good to know. You should know this is how it's happening. Why are we saying print.t.toString? You can just say, because here T is string, if it would be an object, I would have said toString. You can just actually print T also, it doesn't matter. T.toString and T is same. There is a function called persist. The reason I'm mentioning persist here is because we are discussing shuffling and then partitioning. I think in the last session also I went over over how persist will work, but we'll revisit it here. So once you use persist, then Spark will not recalculate that RDD. What do you mean by that? I will just try to follow what I'm trying to say. If you don't follow, just put the message in the chat. So let's say I'm reading data from a database. So that's my RDD1. Then applying filter, it becomes RDD2. Then apply aggregate, it becomes RDD3. And after RDD3, I'm saving that RDD3 to a database. After saving RDD3 to database, I'm applying some more operation over RDD3 and some more aggregates over RDD3, it becomes RDD4. Now I'm saving RDD4 also into a file now. So when I save RDD4 into a file, this is an action. It will trigger everything from RDD1, 2, 3, and 4 again. When I created RDD3 and saved the RDD3 into a database or into a file, that had also triggered RDD1, 2, 3 again. So any action I do further, all will trigger, I'll recalculate RDD1, recalculate RDD2, recalculate RDD3, recalculate RDD4. Any action further on will keep recalculating this thing again and again. So again, I will reiterate. I created an RDD1, apply some transformation, created RDD2, then I created RDD3. I'm saving that RDD3 to the database. The moment I save RDD3 to the database, it will calculate RDD1, RDD2, RDD3, then it will save to database. Now over RDD3, I created some more transformation. I ended up creating RDD4. Now I'm saving that RDD4 to a file. The moment I save RDD4 to a file, it will end up creating RDD1, RDD2, RDD3, and RDD4 again. So if you see RDD1, 2, and 3 are getting created multiple times for each action, which doesn't make sense. So one I can do is I can say RDD3.persist. The moment I say RDD3.persist, then I am saving RDD3. Save it to database. Then it will save RDD3. It will not calculate RDD1, 2, 3. It will calculate once because the first action we are executing. It will create RDD1, 2, 3, and then save 3 into the database. Then I'm applying some transformation of RDD3 and creating RDD4. Now and saving RDD4 to the data to some file or database again. Now RDD4 action will take from RDD3 only. It will not trigger RDD1, 2, 3 because RDD3 was persisted. It will take from RDD3, apply the transformation RDD4, and then save directly into the where RDD4 was getting saved. Okay. So that's the advantage of persistent cache. I will have some more explanation of persistent cache, not in this slide, but in coming session you will see there's a persistent, there's a cache. What's the difference between these two? I have explained it in a different slide. Yeah. So Anshul, your question I already answered. So I'll explain this in different slide. RePartition, you can, and we discussed that. This is one example. Just keep this when you are looking into Spark job for performance, and you will end up spending time you spend a lot of time in fixing the Spark performance. That's where your majority of the time might get spent. So let's say I have one user table which I've read and a RePartition on user ID. Now I'm joining the user on address. Now when I say join and show, now it is it has shuffled. First shuffle is happened for this user table for sure. Now I'm joining this user table again with some other data set. Let's say salary is another data set. Salary just an example I have given. It can be any other data set which can be joined with users. I'm joining user with salary. Now Spark is intelligent enough to know that user has already been shuffled and shuffled, and these are the partition which has user records after shuffling. So it will skip the shuffle for user at least. It will make the shuffle for salary data, and let the salary data set data will go to the partition where user data is, but user will be shuffled only once. But at least first one shuffle of user will be there because you are joining this. That will be there. Now another thing is RePartition. If repeatedly shuffling data on certain keys. Now this is one way to let's say I need to keep joining this user and addresses and users and salaries. So I need to keep doing such things. So this is an improvement, and not many people know it, by the way. So if I'm doing repeated shuffling data on certain keys, then save the data is bucketed table only. So bucketed table is a provision which Spark provides, and I will give an example also. What it will do is it will write the data out already in pre-hash partition. So it will create the save the data in the partition, already partitioned only. So when you read the data back, while reading the data in and join them, you can avoid shuffles. Let's say take an example. Users I have read, and I'm saving the users data set or RDD or data frame in bucket by, and this is the number of buckets I'm giving, and this is the user, this is the columns over which bucketing is happening. And I'm saving this as a, and I have to use save as table and give the table name. Address also I'm saying that, this many number of buckets, and the bucket, this is a column over which bucket should be created. And I'm saving this as a address table. Now I read it back. So this is the user table I saved. I'm read spark.read.table user. This is the same name I'm giving here. Spark.read.address, I'm giving the same name. Now you're joining user.join.address, and you show there is no shuffling. There's no shuffling involved in this, because these data were read in the pre-partitioned way, and you're joining on the same. And there's a condition to avoid this. It should fulfill this condition to remove shuffling. What is that condition? Table should use the same bucketing. What does it mean by that? The same number of buckets and joining on the same bucket columns. So you should save. You should use the bucketing column as same in both of these, and the number of buckets should be same. If you do this and I join these two data sets like I'm joining here, then no shuffling will be involved, and that will be a tremendous performance improvement. Let's spend 2-3 more minutes to discuss the partition types. There's a hash partition, range partition, and custom partition. Hash partition, we discussed it already. Let me skip this. We'll discuss it's already 6:30, so let me stop it here only. And I think I don't want to waste more time. We'll discuss this in the next time, because it will become too much for you also otherwise. So I'll stop it here, and let me pause the recording, and I'll open up for any questions you might have. Just give me a second.